You know that deep learning models work on NVIDIA graphic cards only, right? Do you know? Do you know the GPU, the TensorFlow and PyTorch work on NVIDIA graphic cards only, faster on NVIDIA graphic cards. If you execute on CPU, it works, but it will be slow. You know that, right?
Yes, sir.
So to make, even though the hardware is available, to make the TensorFlow and PyTorch use this GPU, you need to install NVIDIA drivers for the GPU, and then you need to install CUDA API, right? CUDA API is the API that's a linear algebraic API that runs, or that was built by these NVIDIA guys on their GPU. They built a API called CUDA, and then that API need to be installed. And there is another framework called as CUDNN. CUDA, the deep neural network architecture, that the code that actually uh, takes the weights and then calculates the linear combinations and then substitutes into activation function. That whole thing, right? That whole calculation thing happens using CUDNN and CUDA. So we need to install appropriate versions. So these guys said 11 here, and I installed 11, and it is actually looking for 10. One file it is looking for 10, and rest all it is looking for 11, and it's not loading the GPU. And one more problem with this is one more problem with these deep learning APIs is old GPUs they will not load. My GPU is around 1.5 years old, and it is um, GeoForce RTX 1070 version, and somehow it's not recognizing. The GPU is not. So I showed you, right? Last time when we were actually trying to execute, I showed you that GPU was not working. Right? How to see GPU is working or not? So there is a command called as NVIDIA SMI, NVIDIA SMI. So I don't have I actually removed all that junk yesterday I installed. So I'll install that. If you type this command, it will actually show a table how much memory, how much RAM, sorry, how much processing power of the GPU is being used, right? So there is a lot of struggle in setting up the GPU environment itself. So that's where, right, if you have a machine, you will know the problem, because in real time, when we build something, we, on our own, not the cloud-based models. That if you build something on your own, we should know all these things, and we should know the time it takes to set up a machine. At least one day it takes. Okay, if you are lucky, right, maybe it will be done in 1 hour. But if you're not, then it takes at least one day. So these guys actually gave it for Ubuntu 18.4, and I yesterday installed Ubuntu 20. That's not a problem, right? Versions are not supported and all that is there. I don't know whether I have to remove this 20 and then go back to 18, or I'll just try today. Okay, but the models I built yesterday were, I used ResNet architecture to do face detection. Okay, I've taken one data set from internet and then did a face detection model. I'll come to this, but first let us look into the word embeddings and glove model, and then come back to face detection. Okay, so why am I telling you all the stories? You can take this code and execute it on Collab. No need to set up on your machine, but whatever work I did, you can use it, and you can actually execute it on Collab and make the model work best. Okay, so maybe the architecture may not be right. You can actually fix that also. I'll show in a moment. Okay, so yesterday we were actually talking about SVD based word embeddings, singular value decomposition based word embeddings. When I say singular value decomposition based word embeddings, when data is very low, right? Deep learning models need huge volume of data to train. When data set is small, then this SVD based embeddings will be helpful. Okay, so I have taken, I enjoy flying, I like flying, I enjoy NLP, I like NLP, I like deep learning, and I like, I think I enjoy it. Right? So here, right, if you look at I and flying are surrounding words, like and enjoy are similar words, right? I and NLP, I and deep learning, right? So I enjoy NLP. Okay. So there are like kind of, if you look at this, right, it's like flying, NLP, and deep learning belongs to one kind of thing, right? This is related to one person, right? One person maybe, and then the likes of that person are kind of similar. That's how it is taken. Okay, and like and enjoy are kind of similar words. Okay, so yeah, if you have more context, more text, right, it will be more appropriate. But the point is, flying, it is like, so if you have like, I like mango, I like pineapple, I like banana, I like, those kinds of words, right? Then all these, banana, apple, all those things will be kind of similar words. It will actually figure out. Maybe we'll take that data set also, try to execute and see. Okay. So let me take another data set. I'll comment this out, but just comment it out, and then I like. Right. Any other fruits I like? This is the kind of data we find in our data set, right? Then it will actually identify that all these banana, orange, apple are all kind of similar words. It should identify. Let us see. Okay. And any other fruit names? Grape.
Watermelon.
MELLON.
Yep.
Melon. Right. So I will run on that also. First we'll run on this this existing whatever data. Okay. So yesterday's mistake is covered, and I'll let you know. So I have created the corpus here. This is corpus, and then I'm extracting the distinct words from the corpus, and index of like is 3, right? And then I am kind of creating a co-occurrence matrix. You know what is co-occurrence matrix, right? So co-occurrence matrix means I and like how many times they occurred together. Enjoy and flying, how many times it occurred together. So that's now I'm forming that using this code. Right? So this is the data frame. Right? I and enjoy occurred three times together. Like and I and like occurred 3 times together. Right? Now this is a data set, and then I am converting it into a NumPy array because I am going to pass it to SVD. Right? Full matrix I said because it's SVD. It's a full matrix. False I said. I don't know. Let me see what is the full matrix. So there is truncated SVD, another model which is going to work on huge volume of data. Okay, if you have a bigger data set, maybe 1,000 documents, then you should take truncated SVD. U and VH have the shape of a M by M. respectively. Otherwise, the shape will be m by k and k by n. Okay, okay. So, okay. So this is like, rank of a matrix, right? So if you say full matrix is equal to true, it will actually take the, take m rows by m rows and n rows by n rows shape for VH and U, and U matrices. If not, it will actually do the rank of the matrix kind of, whatever the size. So how like, what is the size of ultimate u and v is going to be decided by this full matrix is equal to true or false. I'll come to that later. Okay. So now I actually did SVD, right? Right. I have got these these vectors. So these column vectors are actually the u vectors, and in we are going to take u vectors, u or v we can take, but u vectors will take the column vectors. And then in this matrix, right, in this SVD, we have u, s and vh. S is going to explain each of the vector how much essence it extracted, right? Each of the vector how much essence it extracted. And it is going to be bigger number beginning, a little lower number, a little lower, little lower, and little lower, and like that it's going to be, right? The most of the extract will come to first vector, the second best will come to second vector, third best will come to third vector, like that, right? So now if you want to reduce the word embedding size to 3, we should take 3 values from here and multiply these 3 values with this matrix, you get the vector representation. That's what the mistake I did yesterday. So I have taken this one dimensional array, right? This S, this sigma, right? So U sigma V transpose, right? That's the decomposition. So U matrix will have the word vectors, and then this will have essence. When you multiply, how many number of dimensionality you want. What is the dimensionality? You want 3-dimensional vector to represent your data. You need to take first 3 columns from the S matrix. Right? I took this one-dimensional matrix and converted to diagonal matrix, because the sigma matrix is going to be diagonal matrix. Right? See, all the lower triangle are all zeros and upper triangle zeros, and we have diagonal values. I want k is equal to 2. So I took 2 columns from this diagonal matrix and then multiplied these 2 columns with the u. So I got a 2 each of the each of these words. Okay. So let me see whether I got like and enjoy the same indexes or not. Enjoy is 1 and like is 3. 1, 2, 3. Yeah. So I have taken that and and then I've taken what? Yeah, they both came. Okay. So this is the, so embedding 1, right? Embedding 1 means this row is going to represent enjoy, right? This row is going to represent like. So let us see whether they actually are have came close or not. See that they came close, right? Even these 4 and 5 also came close. What is 5? What is 4 and 5? Let us see. 0, 1, 2, 3, 4, and 5, right? These two also came close. Okay. When I am saying close, the cosine similarity is coming 1. Let me try to see, 1 and 2, what happens. Right? They are different. 1 and 2 are different. The model identified the vectors as different vectors. 1 and 2. What is 1 and 2? I and enjoy. No, enjoy and flying, right? They are different. Enjoy and flying are different. Okay. So here 2 things it identified. Enjoy and like are kind of similar. That's one thing identified. The second thing it identified is identified are trying to create similar vectors for are the ones the person likes or enjoys. Right? So the NLP and deep learning are kind of similar. So now I am actually taking the vectors and trying to represent in a, see this NLP, deep learning, everything came as a, I think I have, yeah, how many words there? Distinct words, how many? 1, 2, 3, 4, 5, 6, right? So actually enjoy and I think flying, NLP and deep came to one place. Flying, NLP and deep came one place. This one I think. Enjoy and like came at one place. I also merged into one of these, I think. Got it? Now does it make sense? Does it make sense? Any questions? Right? So we took the words and converted them. See, I came here. See that I is a different one, and deep learning, NLP, flying are a kind of similar words. A kind of similar words in a way the person likes them. Right? Enjoy and like are similar words, and they came to one place. Got it? Any questions? Okay, so I'll upload this and have a look at it. Right? Basically, yesterday we missed out this. We extracted essence, but we did not create the necessary necessary embeddings there. Okay, so this makes sense. So let me take the other one. Let me comment this out, and let me take the other one. Let us run this and see what happens. I think like and enjoy. Oh, enjoy is there somewhere. Where is enjoy? Let me put everything as like only. See, word embeddings, you're understanding now, right? See this, all fruits came to one place, I at one place, like at one place. The vectors all are, similar vectors it created. For all fruits, it created a similar vector, right? Got it? See, we can actually find out um, what you call it as named entities. Try to do if the data is this structured, if the data is this structured, that's another limitation for the word embeddings is that if the data is structured and grammatically correct, then it works well. If the data is not structured and grammatically formed well, it may work here and there. Okay, it's not that you can do everything right. Got it? Okay. So this is good. I think we yesterday I actually kind of somehow found it this mistake I was doing for last 2 years or 3 years. I think that's a bad thing, but no, fortunate or unfortunate, nobody really notices that, or they may not be using it also, because there is word to vec glove, and even nowadays we have transformer networks. SVD based thing nobody is working. Basically that's where I never got caught. Got it? So this is good. This is the final the best one. If you don't have any questions, right, I'll jump back to face detection, face recognition. Okay, so there are pre-built models like FaceNet, right? In there you will have in here, right? You will have a tool, a pre-processing tool that actually takes the image and converts into 128 pixel 128 dimensional vector. Okay, you can take those 128 dimensional vectors and save it into database and use them. So I tried to use ResNet and try to create that 128 pixel generating network. Okay, so I took Yala faces. This is actually, there are 166 images for of around you know um, 15 different people. Okay, 15 people have taken their pictures, right, like this, right, and then they kept it in a drive. Okay, so I have actually farmed a data set with this, right, 166 images. Each of them is like 224 by 224 by 3. Why 224 by 224 by 3? Because I am trying to use either ResNet 50 or VGG16's architecture to actually train, because the VGG16 and ResNet 50 are already trained on 1,000 different classes, and they are all trained on images. So my feeling is that those weights may help me in figuring out the different phases very easily. Okay, so here I took it and then I wrote some code here to farm pairs. Right? Yesterday I have shown you, right? So like this. So this is a pair belonging to the same phase, right? This phase and this phase are same, right? That is one. The target variable is one. This phase and this phase are not same. The target variable is zero. Like that I farmed, for each image I farmed 5, right? There are 15. There are 15 different phases. For each image, I formed 5 positive and 5 negative records. Got it? These kind of positive records I formed 5. The same person's other picture, 1. Same person's other picture, 1. That's the target variable. 1 is target variable. So same, this person, a different person, right? Target variable 0. Like that, 5, 5, 5, 10 pictures for each. No, 5 positive samples and 5 negative samples I created. Initially, I started with 5 positive, so 1 positive, 1 negative, but it looked like it was not working. So I increased the size, but now the next problem is that the GPU is not working. Today I'll try to make GPU work and run it, right? So this is the network I found. Okay, this Euclidean distance, right? Let us leave that aside. We'll see that later. So input tensor, I have taken 224 by 224 by 3. And then ResNet model I have taken, right? ResNet 50. Residual blocks, right? ResNet 50 has got 50 layers with residual blocks. Each one is like that AL plus 2. AL plus 2 in our ResNet. Okay. So the kind of that 50 blocks will be there. ImageNet include top false I kept, because the target variable, the output layers I'm going to define. Okay, and then input tensor I have taken, and I found I actually found a dictionary so that I can make the ResNet model layers trainable false. Right? I don't want to train them again because it's a huge network and my machine cannot handle it. So I have taken the output layer and then appended, I flattened it, and then that flattened one passed into dense layer, and that dense layer passed into 128. So basically, this is the network I need. That's the network I need. Okay, you got it? This is the network I need. Okay, and then taking this network, let me open that FaceNet model. See this network I built now till here. This network or this network. Any picture you pass, it will give you 128 pixels. This network I formed now. Getting it, Srisram?
Yeah, yes, sir.
Right? That network I formed. You know, don't look at Euclidean distance and other areas. Only this part you look at it. That's this network. That is this network. Okay. Now what I'll do, I'll pass this picture and this picture, and then pass the output, right? These outputs into sigmoid node. Before passing that into sigmoid node, I am calculating Euclidean distance here. This diagram is wrong. Here I should put Euclidean distance and then pass it to sigmoid node. That's what I'm doing. Right? Okay. So and y is there. So what is happening here? When same picture is passed, these these weights are getting adjusted in such a way that you get one, right? The outcome of these neurons, these layers will give you the numbers that will give you 1 in the output. If the pictures are different, it will give a number 0 in the output. So that way these weights will understand whether it is same or not. If it is same, these numbers will be in some in certain form, and if they are different, these numbers, these 128 numbers will be in different form. So for each, when once it understands, this network understands the whole pattern, you take any picture, pass it, and take 128 pixels and save it into database. And new person comes in, you pass into the same network and take the 128 pixels, check against database. If you find closest match, you say the person belongs to the office. If not, the person doesn't belong to office. So if a new person if a new person comes in, right, no need to take the whole data and train. Take that person, create a positive sample, create negative sample, pass it through the network and train it. That way, this 128 pixels will be generated. Okay, the basic thing is you pass the person and generate 128 pixels and save it into database. That is one way, right? New person came in, you take that picture, pass it into the network and generate 128 pixels and save it into database. That works. But if it is not working, then you have to take the data and then retrain the model. If you, I think you have to take the whole data and retrain. If you don't take whole data and retrain, right, model will forget the existing pictures. So basically, if you have good enough data, maybe 2000 people and maybe around 50,000 samples, and you trained a model, like quite decently, then any new picture you get, you pass it through the network and create 128 pixels, save it into database. Person comes in front of the camera, you take that picture and pass it to the same network and generate the pixel that whatever, and then check against the database. So this is like a model that generates 128 pixels. Our goal in phase, the Siamese network, is to generate a model that generates a embedding for the picture, encoding for the picture. Got it? That's the goal. Okay, got it, right? So I generated this, I actually wrote this network. Now I am actually creating this network. Okay. To do this network, what I need to do? This picture, I need to pass it to this network. This picture, I need to pass it to the same network. I'll get two, and then I need to merge them together. See this here? Input anchor phase, input positive or negative phase. Okay. This is input anchor phase, positive or negative phase. Here in the picture, it is negative phase. Okay. And then phase encoder model. What is phase encoder model? This is the model. Right. In this, I have taken resonate models input, and then I am taking output as my output. This is my output. So it's going to take the input and go through the resonate, go through the go through the resonate, and come back, come to this my network, and it will output. Okay, it will output this 128 pixels, right? And then phase net model with a positive or negative image also. Okay, I have got two this kind of networks now. I am combining them with Euclidean distance and then passing it to sigmoid, right? And then model I am training now. right? The model I am training now. So I was not getting more than 50%, around 55 to 58% accuracy I am getting. More than that I am not getting. Especially when I took one positive and one negative sample for each of the picture. So I changed it. I actually kept it like, more. So more means for each picture, 5 positive samples and 5 negative samples I have taken now. So let me try to put this, wait. Right, batch size also matters. If the batch size is high, the memory may not be sufficient. Okay. So let me run this, let me run this. It will be running, and in the meantime, right, I'll show you BGG16 also. The same network I created with BGG16 also. You see the same code, everything is same. Even input size is also, input dimensionality is also same. Okay. So positive sample, negative sample, and then this is VG16. That's it. Okay. So I am actually trying to show you how to use pre-trained, pre-existing models to create your own, whatever model. So I showed you FaceNet here, right? Somewhere. I don't know. I closed it. Yeah, FaceNet. So this FaceNet, if you can, if you can take this architecture and create it like, maybe let us see FaceNet. In PyTorch, right? We have all these famous models embedded into PyTorch, and it is easy to build. You can do it. You can do it on your own, right? FaceNet. Model Zoo, Model Zoo, Model Zoo. FaceNet is not there. So you can actually take that architecture and what is this? Open pole mark PyTorch, cyclic GAN and pix to pix. Oh, something I found here. See, this YOLO TensorFlow model is slow compared to PyTorch. PyTorch is fast. We are using PyTorch only. Okay. So this is the model Zoo. I think we don't have FaceNet model is not there. If you have FaceNet model also here, right? Like that, like this, you can actually take this, take the FaceNet model, and then lock the layers which we don't want, and take the top layers and take your own pictures and train. I am always talking about custom model because pre-trained models will not work for our requirements. You need to remember, pre-trained models will not work for our requirements. You can create prototypes, POCs, but if you want to build a real-time, real running project, right? You should know how to build custom models. That's where I was from the day one, right? I'm talking about model zoo and try to understand object detection, API and all that, right? Because of that. Is this clear now, Sasiram Garu? Now what I'll do, when a new picture comes in, right? I'll take one of these network face encoder model and then pass, like this. When a new picture comes in, right? This is what is the output of this network? It is 128 pixels, right? So I actually convert the picture into these dimensions. Right? Convert the picture into these dimensions and pass it to face encoder model. That's it. I'll get 128 pixels. Now for all the maybe 7-8 images, right? I'll actually do the 128 pixels and then save it into database. A new person comes and stands in front of the camera. I take the picture, pass it to this, and take the 128 pixels and then calculate the Euclidean distance. I thought of doing that, but this model is not working well. So it's 51, right? Again, it's around that 50 only. It is actually oscillating. Maybe because data is low, right? Data set is small. So we can take huge data set. There are huge data sets also in the internet. So we can take them and try to work with it also. The same code will work. Okay. Any questions? Are we good? Okay. So let me jump back to the word embeddings. So we have actually seen this SVD based embedding, right? So by selecting k singular values, singular vectors we will select by multiplying with this this S matrix. Okay. So I have given this PDF also, original PDF from where I actually looked into the content and prepared. Okay. So even the sentences I have taken from there. So this is a co-occurrence matrix. So these are the problems with this. Okay, the dimensionality of the matrix changes very often. When a new word actually comes in, right, the dimensionality will change. Okay, matrix dimensionality, the original matrix will change. If you have 6 words, you'll have 6 by 6 matrix. If you have 7 words, 7 by 7 matrix, and then you need to run this SVD again. Okay, the matrix is extremely sparse since most of the words do not co-occur. Okay, and then matrix is very high dimensional, right? Like this. When it is high dimensional, you never go to SVD. You may go to the word to vec kind of a thing. Okay, quadratic cost of training. Performance of SVD is not that good. Then you have to take truncated SVD, and it is not, exactly SVD. It is a kind of SVD. Requires the incorporation of some hacks and annex to account for drastic imbalance in the word frequencies, and some solutions to ignore functional words. Ignore functional words such as the, right, the stop words you can ignore. Apply a ramp word. So this is another technique. See this here. Weight the co-occurrence, right? The co-occurrence, we are actually taking it as the count. If you look at this, now I like occur twice together, so we kept 2. Instead of doing that, we can actually calculate the distance, how many words apart, 2 words or how many words apart. Based on that, you can calculate the score. Not to make this matrix a sparse matrix. I like deep learning, right? I like NLP maybe. NLP and I are like 2 words apart, so you can calculate some score there, and maybe 1 by 2 or something like that, 2 by 2, 1 by 2, something like that. Instead of having zeros, right, you can have some number there. Okay. Yeah, Pearson, use Pearson correlation. rather than the counts and all that. These are all kind of workarounds, but if you frankly talk about these word embeddings, right? They'll not work perfect. Okay, unigram, bigram models also you can do. So try to read this paper, because this is not a big article, 10 pages only, and in this itself we have this uh, word to vec and glove also, right? I think word to vec is there. So you already know word to vec, you already know SVD. Just try to read this article. Okay, you will get more clarity, or sometimes the terminology becomes more familiar. Okay, so that is about the SVD. Now let us look at the glove model. I'm not going to take much time here, because word to vec or glove, they both work similar. Glove was found by the Stanford guys. They took the word to vec and they took SVD, they mixed it up and tried to create something else. Okay, so it's not a big deal in my view. Okay? So and there are no models built for glove, and we need to convert the pre-existing uh, pre-existing pre-trained vectors are there, which are created by Stanford guys. Only that is the source. There is no class that actually gives us flexibility to train our own word vectors. Word2vec has got a code, right? You have seen that, right? GenSim has got Word2vec model class. You can pass your corpus and then train and get your own vectors. But for glove, we don't have that. Okay. So I'll show you where I'll get and where we'll get, and I'll show an example also. Where did we use it also? So SVD model will not scale with bigger vocabulary, that we know. SVD model considers either co-occurrence or correlation only, but word to a kind of model will capture more than co-occurrence. It's like more than co-occurrence, and it is actually n-gram model kind of a thing. It is not unigram or bigram kind of a thing. Okay, glove is a combination of both, right? Word to vec and SVD. Okay, so here the base of this glove model is the cost function. So
Sir, I think you are sharing something else.
really,
Yeah, we are still seeing that PDF.
glove, you don't see glove?
No.
Let me stop and reshare. You can see right now. Can you see now?
Yes, sir. No.
Yeah, I think it got stuck. This, Zoom is best, compared to Google Hangouts and this Teams and all. It actually takes less space, and even recording also it takes very less space. But that guy is not allowing us to register a new account. I closed it. India China stuff, right? I closed it, and that guy is not allowing me to open new account now. So without China, world will not run. It seems. It seems. Okay, so the cost function is the basis for this glove. Now it actually takes co-occurrence counts WIWJ. This co-occurrence matrix it takes, and then there is a function, right? F of Pij. Pij is the probability. They are taking count as the probability, right? I said count and probability are kind of synonyms in the beginning of the class, right? Because the denominator is going to be same, numerator is going to change, something like that, right? So they are saying Pij, this count as Pij for a word and other word, ith word and jth word, the whatever the number we are getting is the Pij, and then function of Pij to scale most frequent words coming, combination counts, right? This is like TF-IDF, right? Most frequent word combinations, it's going to reduce, the importance a little bit. I don't think it is needed, so they're reducing it, and then theta is the parameters, right? It's the learning actually, all parameters that actually learn, and then ui vj, learnable weight vectors. So these are the vectors that actually ultimately learn. Okay, and then you take embedding as the vi plus vj. In our word to vec, what is happening? The learning are the weights only, right? You have taken one hot vector, and then for each word, let me try to show that and talk. So for each word, only that set of vectors get trained, and you take those weights as the representation for that particular word, right? Embedded representation or encoded representation for that particular word. Here also in Glove also, I did not pictorially show it because it's a research topic. I need to take another month again to draw that whole thing, and it is not needed because anyway we will not be using this much. We may use word to vec and maybe transformer networks, embeddings from transformer networks. So for interview purposes, I am explaining this. Embedding is going to be ui plus vj. Whatever the learner parameters we have got in the network, we'll combine them and represent each word. Okay, so these are the things we need, and the cost function is actually going to pressurize the network to reduce this cost. What is this cost? F of pij is what? Most frequent words combination count. It's going to reduce that some function. It is TF-IDF is a function, right? TF is a weighted term frequency, 1 plus log TF. IDF is n by df. They're all functions, and you multiply those two, it's a TF-IDF. That kind of a function it is. You don't care what the function is, right? So these many times occurring. There is 1,000 here. I like 1,000 is there. It tries to reduce the 1,000 to maybe 10 or something like that, because beyond a certain number of co-occurrences, it is not that important. If you give more importance, the vectors may get generated wrong, right? It kind of works as noise. Do you agree? Beyond a certain number of co-occurrences, it is not that important. The co-occurrence is not that important. If you have bigger numbers in particular cells, those co-occurring words will actually act as noise and try to deviate the embeddings generated. Do you agree? It's all theory, right? You need to think and understand.
Yes, sir.
Right? So if you understood the word to vec well, right, and the TF-IDF well, you will understand this theory well. Whatever the person is actually talking about. If you don't understand those two, this is like Greek and Latin. I am actually talking something, and it doesn't make sense at all. That's where the fundamentals are very important. Okay, so if not now, you will get it in a month, because anyway you start reading through all stuff and doing a lot of stuff in this month. Don't leave it. Try to spend at least 4 hours a day, if possible, right? At least 2 hours a day, if possible, right? So at least 1 hour a day, you will get it, because we covered all that is needed, and it's like research work I did. Right? If you want to write a research paper, you can do it now, but it takes time. I am not giving you the whole thing that will enable you to that will actually right away give you to do research, but it enables you to do research. Okay, so this is a function, and then u transpose v, right? This is the vectors, right? The trainable vectors minus log of pij. What is pij? The count, right? So you have sigma, ij is equal to 1 to w, right? So for all words, it will actually try to calculate this. These weights will be randomly chosen first. ui vj will be randomly chosen. These numbers are already there, right? Pij is there, f of pij is there. Do you agree? F of pij is a function which takes pij and calculates. Pij is already there, so this term are already there, right? And then u v are the ones which we need to take, right? They are going to be random vectors. For each combination, it's going to be random. For ij combination, U is going to be random and V is going to be random. Okay. Now you calculated random and there is going to be too much cost here. We are squaring it because we don't want to have cancellation effect. When you square it, all that error, whether it is negative or positive, is going to get added to this total j of theta. Okay? And there is a neural network that actually does back propagation on these weights. Okay, and again it actually tries to calculate, and our goal is to reduce the gap between this UI VJ and log Pij. Our goal is to reduce gap between these two. What is Pij? Is the co-occurrence count, right? If the co-occurrence count is high and your UI VJ are coming close to it, that means UI VJ are understanding the pattern, right? Do you agree? If you look at this cost function, that's the key. In Glove, how Glove works, that's the key. Pij is high number and UI Vj are random chosen vectors, and you are adjusting those vectors and coming to a place where the gap between these two becomes 0. Does it mean that UI Vj can represent the Pij? Does it making any sense, or it's like I am going in my own?
Yes, sir.
Right.
So at the end, the cost should be low, right?
Cost should be low, but the cost is also based on the co-occurrence count, right? Based on the co-occurrence count. We have taken some vectors, some random vectors, and then we are trying to bring them close to the Pij. Right? Pij, why is close to Pij? There may be million words in your data set, right? And million by million matrix it is. This is million by million matrix, and you are actually trying to represent each word as a 150 dimensional vector. So UI is going to be 150, Vj is going to be 150. You multiply, right? You multiply, and you bring it close to. When you multiply two vectors, what happens? You get one number, right? So bring it down to this. You adjust these weights in such a way that it actually represents this number. If the gap is low, it represents that number, right? So ultimately, you can use these vectors as the representation for that particular word. Okay, you take for each word, right? Uij, Uvj, you take as the representation for that particular word. Got it? Objective is to reduce the gap between this thing. This model will utilize ultimately learn UI and VJ both. The model will go over one pair at a time. Okay, it takes one pair and does all the calculation and reduces, and then it takes these two and sums it and takes that as a vector. So we are considering co-occurrence as well as deep learning capability. They say Glove works better than word to vec. Sometimes it is, sometimes not. It depends on data set. Okay. If the co-occurrences are quite frequent and co-occurrences are most important, then Glove works well on a huge data set. But on a huge data set with co-occurrences importance, SVD will not work because of the the calculational the mathematical complexities. So you can take Glove on that, right? Grammatically structured, most frequent co-occurrences, then Glove will work. If the grammatical structure is not there, okay, there is no guarantee. So you need to understand the drawback of the model also. Some people think that word to vec will work and pre-trained model will work. That's a end of ignorance, I would say. Right? They think the pre-trained models which are existing, built by Google or Spassy or somebody, they think it works. It's not going to work. Clearly, it's not going to work. We need to train all those models. To do that, we need to understand all these fundamentals. Okay. So these are the kind of they want to show, right? Show off that it actually works. Semantic, syntactic, and overall. So how on a huge data sets, right? They actually trained 42 billion tokens. Okay. So if you go into the Stanford University's website, we actually used the corpus there. So this is the page where actually they kept some of the pre-trained models here. See this, they actually trained, and man and woman, right, king and queen, kind of, they trained on different data sets, and they actually got these kinds of diagrams. Okay, and then see this here. I think you can see this, right? Common crawled data, crawled data. What is crawling? Do you know? Do you know what is crawling?
Yeah, moving slowly.
Yeah.
Sorry.
Moving slowly.
Yeah, web crawling. This is, web crawling, right? Web crawling or web scraping.
Scraping. Yeah.
Right? It is scraping. You write a program that actually opens websites one after the other, and then tries to extract the data, right? All that content what is present on the website, it actually scrapes it and puts into database. And by doing that, right, they actually took 42 billion tokens and then trained Glove model on it, right? That Glove, 300 dimensional vector it is. When you take either Word2Vec or Glove or SVD, you can specify the dimensionality, right? Right? In Word2Vec, size is the parameter. Size is equal to, you give some number. In SVD, K, right? K number of vectors. You are actually taking two, the sigma, eigen values, and then multiplying those with your vectors, SVD vectors, and then you are getting the word embeddings there. Like that, it is 300 dimensional vector. So this is 27 billion, tokens, and there are 25 dimensional vector, 50 dimensional vector, 100 dimensional vectors, and 200. So there are 4 different dimensional vectors they created. This is Twitter data. This is social media data. Okay, this is common crawl web data. This is okay. So 840 billion tokens. See, so people think that these common crawled data or the vectors will work on our data. No, it will not. It will not. However, most recently there are GPT-2, GPT-3 models. GPT. Right? GPT-3 is not available for public, I think. Yeah.
Sir, when you say size in Word2Vec, is it that 128 representation?
128 or 150, right? In Word2Vec, I showed you 150 dimensional. Yeah, 128 is also embedding only. These guys name it differently so that we'll get confused and we spend time. We waste time. The all scientists have got their own prejudice. They want to make everything big. There's nothing actually. They have to spend time, but the concepts are small. We have to implement it, right? It is very difficult to implement and takes time. I'm saying when there is nothing, it's not literally nothing, but conceptually it is nothing. If you talk about rocket also, conceptually nothing, right? There is some gravity and you are actually putting a big fire behind it and trying to push it. So how much push you should put to reach to a certain place? That's the key, like whatever the major finding, right? You fire it and push it out, it may go into somewhere, right? It may not land on moon. So you actually put the projection and you calculate the direction exactly and do it, right? That's kind of, so conceptually they are nothing. Conceptually, when you understand, right, you will anyway jump in and try to do something, right? So that's my feeling actually. If I don't know what is conceptually what it is, I'll not even dare to go there because I may feel like it may actually waste my time, right? So that's kind of, I try to demystify most of it. I don't know. So GPT is the most famous model now, which is actually trained on too much, billions of tokens, and it is actually performing well. That's what I heard. I never used it. GPT-2 is publicly available, I think, and you can actually take those embeddings. I'll show you how to take these embeddings. So we have used these pre-trained Twitter embeddings and then built a model. Okay, so you can download this, and then you can convert these embeddings into word-to-vec embeddings and use them. So let me show that. Any questions so far? Let me show you. So there is a data set called as Wasim data set. I think this is an exercise actually. It's an exercise, and I did some junk coding here. Don't be scared. You can do your own, right? So let me show you that. So I have taken this Wasim, clean data set. This Wasim data set is a cyberbullying data set. Do you know what is cyberbullying?
Yeah, scolding each other and shouting at others.
In Andhra Pradesh and Telangana, it happens a lot.
Yeah.
For film actors and political leaders, they're all earning and enjoying. The people, ground, they actually waste their time by doing all this, right? So that is cyberbullying. It happens even in the US also, but it is in the close circles and kind of maybe like this also, right? So that's a challenge actually, whether a sentence is cyberbullied sentence or not. Okay, so we are actually trying to classify that, whether a sentence is a cyberbullied sentence or not. So there are data sets there, and I have taken that data set. We were actually trying to help one guy do research, and I couldn't spend time. I kind of spent like around 2 weeks on it, and we had got other work, and we got engaged, and I tried to assign this to some of the students, but nobody showed interest because it's a bit tough to execute. Maybe you guys can try. Okay, so I have taken this data set where I have the word, the sentences, and the labels also. Sentences and labels. You will find all kinds of bad words in this data set. So I cleaned it a little bit, and then I tokenized, right? And then I assigned the embeddings here, right? These are like the. Okay, I need to explain that, I think. Okay. So there are some APIs I used in this. So I'm just. Okay, so there is something called as embedding lookup in TensorFlow. Okay. So what is meant by lookup? Do you know? What is meant by lookup?
Into your table, look at some index and find out some other value.
Yeah, right. You already have the data, and you are actually trying to look it up and then bring it out, right? This embedding lookup is like that actually, right? I actually created a simple example here to show that. So suppose that there are 8-dimensional embeddings of 1,000 words, right? 1,000 words, each of 8 columns, right? Each row is an embedding of a word. 1000 by 8 matrix it is, right? Each word is a numerical representation of a word. Suppose that, right? Suppose that this is already there. You took the data and you did word to vec and you created 8-dimensional vector for each of the word. Right? Then you are actually trying to take the indexes, and then you are, this is the params or embeddings I should say. Right, so let me run this one. So what are we doing here? Embeddings of IDs is nothing but you are taking those indexes, rows, right? Those 5 rows I have taken. 0th vector, 5th vector, 17th vector, and 33. The words corresponding to these indexes, I have taken them. This is what is done by embedding lookup also. Right? If I do the same, let me take the same. Where's params? Okay. See that? Do you see any difference in these two matrices? Do you see any difference in these two matrices? This matrix and this matrix?
They look same.
Same, right? Same, right? Embedding underscore lookup method is actually taking the embeddings from the already pre-existing embeddings. You should actually apply word to vec or glove or transformer network and convert your text into numbers, word vectors, and then use word embeddings lookup, because the embeddings lookup will give you tensor. See this, the difference is this is a tensor. This is just an array. Okay, this is just an array, numpy array. This is tensor. That's the difference. Okay. So to convert your embeddings into tensor, you need to use this embedding lookup. You need to pass your embeddings into a constant, make a structure, make that tensor structure, and then lookup. Just to do that only. Embedding lookup in TensorFlow will not create a word embeddings for your words. Got it? Okay. This clarity is needed. This clarity is needed. That's one thing. And then you have tokenizer in TensorFlow also. It actually tokenizes, and you fit on your text. You can actually put filters also in tokenizers. You can put filters, right? How many occurrences it should have. These kinds of things you can actually put in there. Okay. So this is a simple example I have taken, and then anyway we are going to do the pre-processing using whatever we like, or we write our own code also. And fit on text, I am actually understanding on the train data, and I'm going to take this train data and two sequence. So I am converting the text into sequence. So for each word, a number is given. When I say fit on text on train set, right, it takes tokens from this state from this data and assigns a number to each of the word. So this is first sentence. This is second sentence. Right? Like that. So n sentences it actually assigns each word a number, and that number is going to be carry forwarded, right? It's a unique number given in the total corpus. And on test set, right, if you apply, if you find some word which is not present in train set, it will not know. So you actually have to put those also in there. Okay. I don't know whether I did it or not, but so basically you need to take care of that also. If unknown word comes, you should put like UNK, right? Greater than, less than UNK, greater than kind of text somewhere. Okay. So text tokenizer, sequence, train sequence, sequence to text. You can actually convert a text into numbers and numbers into text. This is just a one number given to each word. It is not an embedding. Got it? You can take that as an embedding also, but it is not intelligent embedding. Got it? Each word given a number. Friend and friends will get two numbers, two different numbers. Friend will get maybe 20, friends will get maybe 300. No semantic similarity, just a dumb assignment of numbers is the text to sequence. Okay, and sequence to text you can actually revert it back because it will have the dictionary present in it. Okay, so I have taken this data and right, I am doing a 150 dimensional vector embedding. See this, I commented this out because when I run the code again, it may actually try to run it for longer. So word to vec I have taken size, embedding size, I think 150, right? And then window size 3, right? Left side 3, right side 3 words I will consider. Min count 1. At least once the word occurs, we will actually take it and do a vector for it. A skip gram is equal to 1, workers 10. Okay, build vocabulary, then train the model. Right? We pass whatever all that. Okay? And I am saving that into a pickle file, and I loaded it. I don't know whether I have it in this machine or not. Right? And these are the vectors, 150 dimensional vectors for each of the word. Now, when you convert each word into a 150 dimensional vector, your data set becomes a 3-dimensional matrix. Do you remember that? See that? Like this. Each word is a 150 dimensional vector, right? There are maximum 1521 words in one of the documents in total data. In cyberbullying dataset, the Wasim dataset, there are many documents. But in one of the document we have 1521 words. So you need to convert each document into 1521 by 150. Did you get this point? Any questions? What are we trying to do now is, I have taken a data set. I am creating word embeddings. Using word embeddings, I am actually building a deep learning model. Sorry, no, I kind of explained many things and then I'm talking. Now we are trying to take a data set, convert words into vectors, then do a deep learning model. This point clear? Can I move on? Let me ask a question. So I said in Wasim dataset there are many documents or many rows, right? And there is one row with 1521 maximum words. I said each document or each row should be converted to 1521 by 150. 150 anyway, it's a word vector. For every word you get 150 dimensional vector, right? That's okay, I think. But why you need to actually convert all the sentences into, even though there are 3 words or 10 words or 1521 words, you need to convert that into 1521 by 150. Why do you need to have a uniform dimensionality throughout all the sentences or documents? Why do you need?
The model will not take different dimensions.
Model will not take different dimensions. Input layer should be of same dimensions, right? So that's where what we are doing is, even though there are 10 words, we are taking 10 vectors. This is the first vector, second vector, third vector, fourth vector. And after the end, right, I'm putting 0 vectors. If 1521 are there, 1521 vectors will come. This is 150 dimensional row like that, right? So this is review 1, this is actually the document 1 or bullying sentence 2, 3, 4. If I take a 4 document batch, right, that's going to become a 3-dimensional matrix. Can I pass this into a machine learning model? Can
No.
I pass this? Huh?
No, it won't take three-dimensional data.
It won't take. This is how it is. When you actually do tag of words or TF-IDF for hashing vectorizer, it gives you a two-dimensional matrix. The whole data becomes a two-dimensional matrix. Whole data. But in this case, right, one document is becoming a two-dimensional matrix. Right? Now, if without deep learning, you cannot do much. Okay. If somebody says that they know word embeddings and they don't know deep learning, that guy actually for fun they did this word embedding. I've seen one researcher who actually does transformer based word embeddings, and then he takes average of that word embedding and creates one number for each whatever one vector for it's like you have taken a review or a sentence, converted each word into a vector, and you took an average of this whole thing and represented that whatever. So it became one-dimensional vector. Is that a meaningful thing? You are actually struggling a lot to find the word vectors, and then you are averaging the whole document and creating one vector. That's a meaningless thing in my view. That's how people are, and then applying machine learning algorithm. They're coming back to machine learning. That's it. Okay. When data is less, that is good. That's what we should do. When data is huge, you should never do that. Okay. This is machine learning, and you can do. But in the word embeddings, right? When you do word embeddings, your data becomes a three-dimensional matrix. So each document should be processed in a different way. I draw the diagram. No, I don't. How will we actually use the one-dimensional convolution? Okay, one-dimensional convolution to reduce the dimensionality of this, and then ultimately to pass it to a deep learning model or fully connected, convolution. So we are at a place where deep learning will not work. Sorry, machine learning will not work. Once you convert your, anyway, on pictures, machine learning will not work.
So
On
there is
text,
a lot of background noise, sir.
oh,
As if I'm
Sorry, it's from my side. Sorry about it.
oh,
Okay.
okay. So the once you convert your words into the vectors, right? The dimensionality changes, and you no more be able to use machine learning. But how to handle it? Let me show you. Let me draw that, and I'll stop here. With the explanation of how to use um, how these one-dimensional convolutions works on images, right? On pictures, we used 2D convolution. Do you remember? Conv 2D, right? We used.
Yes, sir.
Yeah, we are going to on text, right? We are going to use Conv 1D because it works like n-gram model. Why not? I cannot use Conv 2D. That's a question. Let me take that picture. Right now your data became like this, right? So this is review 1. This is review 1, right? Oh my god, sorry. What's happening? So this is review 1. Oh. Yeah, this is review 1. This is
Yeah.
3. You can see screen, right?
Yeah, just now it came up.
Okay. So I am writing something. Can you see?
Yes, yes, sir.
Okay. So this is one batch. You may have thousands of documents in there, but this is one batch you are passing in. Right now, when you apply 2D convolution, what happens? So I am actually showing you the filter here. In a 3D convolution, what happens if the image size is 224 by 224 by 3, right? If you take a filter of size 3 by 3, what happens? Or 5 by 5. The filter is going to be 5 by 5 by 3 because the previous layer channels are 3, it becomes 3, right? In 1D convolution, if you specify filter size 1 or 2, I'll take 2. If filter size 2, the number of columns will be automatically taken. It is going to be 2 by 150 because I just now showed you that each row is a 150 dimensional vector, right? This is 150. Okay. This is 1521. Rows are 1521 and each columns are 150. When I say 1D convolution and filter size 2, it will automatically take 150. So now this filter will apply like that. And the first document it will apply like that. Okay. When I say a 1D convolution is applying like this, what is it doing?
Element-wise multiplication.
Element-wise multiplication and linear combination. So when it applies here, right, what you get? You get one number. Maybe I'll say A, right? And then slides one row. 1D convolution. In two-dimensional convolution, what is happening? If the picture is like this, right, it will actually slide like that, right? And then slide here, slide here, slide here. But 1D convolution, right, it will actually slide here, generate one number, generate another number, right, again slide, generate another number, slide, generate like that. And ultimately you get a one-dimensional vector. A, B, C, like that. So on the first whatever, the first document, the first filter will get applied. Okay. And then you get the one-dimensional whatever, right? And the second also it will get applied. Third also. On this batch, a particular filter will get applied. 1D convolution will get applied, goes forward, does whatever, and comes back, adjusts these, right? Sorry, adjusts these weights, and then again generates, right? And ultimately, it actually tries to predict the y while reducing the dimensionality here. Okay, when I say it is reducing dimensionality, it has got some trick embedded in this. Let me explain that. So when you take a one-dimensional convolution and doing a linear combination here, right, you are considering two words here, right? Two words again. Two words. When I say two words, the vectors, right? Vectors of two words we are considering. If I say filter size 3, right, I can consider three words. Let me take another word. I can take three words, right? Three words. Here, three words like that, right? If I take five words. If I take 10 words at a time, that's the flexibility. Right? When we were actually trying to do bag of words with n-gram model, beginning and end, we were struggling a lot because it might occupy lots of space. But here you can do 2 gram, 3 gram, 4 gram, 5 gram and merge them together. So you can take this as a 2 gram model. This is another 2 gram filter, right? But you can take 3 gram filter there. Right? This filter will generate one-dimensional vector. This filter will generate another one-dimensional vector, like that. If you take n number of filters, n number of one-dimensional vectors will come as the output. And you pass this to another one-dimensional convolution, or you can pass it to flatten it and pass it to fully connected layer. Got it? How 1D convolution works and how is it helpful in doing n-gram models on text? Got it? Yes, no? So
Sir,
I'll
how-
show you. Yeah, hold on.
So when we do the flattening, these number of one-dimensional vectors will be converted into single vector.
That's it. Yeah, that's it. Okay. So let's meet tomorrow. It's already 9:10. So let's meet tomorrow, and I'll show. I'll start with the same theory, and then and we'll see the code.